So in this video, let's look at the situation where we have two masses on an inclined plane connected by a string and a pulley, and there's going to be motion either up or down the plane. So let's have a look at finding the acceleration of the two masses, given that mass 1 descends. But we can look at the general situation. The acceleration could be down, it could be the particle on the plane accelerates downwards that way, or M1 accelerates down. So it could be M2 going down or M1 going down, but let's just have a look at the general situation. Okay, we have an inclined plane, we have a pulley, we have two masses, M1 and M2, connected by a string. The string is light, so its mass is negligible compared to the masses M1 and M2, and doesn't need to be taken into account in the calculations. We assume the string is inextensible, which means it can't stretch, it can't deform in any way, so that the tension here is the same as the tension here. And that's very important. A light, inextensible string is always the assumption in these sorts of problems. Okay, again, for the masses, we use our particle model, where we imagine all the mass concentrated at the geometric center. And here's our geometric center, and all the forces act through that point. So that's where we draw the forces. Same here as well for the mass M1. Imagine the geometric center there, and all the forces act through that point. Now, each mass has its own coordinate system. If you look at M1, for instance, we have to the right and up. So the I is in the horizontal direction, J is in the vertical direction, aligned with the page in front of you. Whereas for mass 2, the coordinate system is the surface of the plane is the horizontal direction, and the surface of the inclined plane is the horizontal direction, and then vertical to the plane is the perpendicular direction. So these are two different coordinate systems, but they'll be connected by the fact that physically the tension in the string here must be the same as here, and that is what will connect the two. But they are two different coordinate systems, so perhaps we should really label one as J prime and the other I prime. So we have I and J and I prime J prime, because they really are two different coordinate systems. The inclined plane makes an angle of theta with the horizontal axis in the primed frame. And let's have a look here at the various forces. We have a friction force. It acts down this way. If M1 moves down, then M2 moves up the plane, so friction will work against it, and so that tells us the friction force is this way. If for some reason M2 were to go down the plane and M1 were to go up, then friction force would act up the plane. Okay. The tension is to the right, it's up the plane in this case here. And we have the reaction force. The mass doesn't accelerate off the plane, it doesn't accelerate into the plane because there's a reaction. The plane pushes back up on the mass with an equal and opposite force, that is the reaction force. Label that R, that's perpendicular to the surface of the plane. If we continue the line in the direction of the reaction force down into the plane, okay, then we find that the weight force, that's the weight force acting on the mass M2, is directed vertically downwards in line with the negative direction of the J prime coordinate system. So down towards the center of the Earth or whatever body this is taking place on. Okay, let's start with M1. Okay, so for M1, okay, in the J, and we should say prime direction, and also, okay, so in the prime direction, we have here plus T. T is up in the positive direction. Remember, we chose positive here. And again here, this is positive and this is positive. Very important we do that because we need to sum all the forces to find the net. Okay, for M1, okay, then in the vertical direction we have plus T, and the weight force is acting in the negative J prime direction, so minus M1G. We're told that M1 descends, so we can say that the net force must be down. Okay, if there's to be an acceleration here, then the net force must be down. If the mass for some reason stays where it is and there's no movement, then the net force is zero, so all that's zero. Even if this were to move down or up with constant speed, then the net force would be zero, and this would be zero here. But we're told that there's an acceleration and m1 will descend. So it's going to accelerate down. m1 will accelerate downwards. So the net force will be minus, in the minus direction, because the net force is going to be down, it's minus m1 times a. Okay. For m2 in the j direction, for the second mass, we have the reaction force in the positive direction. We've chosen up to be positive. And the weight force, what we now need is this component of the weight force. Remember, there's a component parallel to the plane, this one, and there's a component perpendicular to the plane, this one. And the perpendicular component will be m2g cos theta. Okay, if you think of this right angle triangle here, here's theta in here, this is cos theta is the adjacent, this force here, okay, over the weight force. Rearranging that, m2 will give us, so if I do it like this, here's theta, okay, this is mg, it's this one here, okay, and this one here is the J component, if you like, of the force. Okay, then cos theta will be adjacent on the hypotenuse, and so rearranging that will give us mg cos theta. Okay, now it's in the negative direction, so we're going to put m2g cos theta, put a minus in front. Now, the net force in this direction is zero. The mass doesn't accelerate off the plane, it doesn't accelerate into the plane, the net force is zero, so that's zero. Okay, let's have it. From this immediately, that tells us that the reaction force is m2g cos theta. All right. Now, we go down a little bit further. On the plane, in the I direction now, okay, we're going to have, we know that we're on the plane because of the friction forces involved, okay, we're talking about this one. Okay, so we have, if I can just show you again, in this direction, up and down the plane, in the plus direction, we have the tension force. In the negative direction, we have the friction force, but we also have this component here. And this component is m2g sine theta. Remember this one, sine theta, opposite over the hypotenuse here. Same calculations, all this here. Okay. So what we get is tension up the plane, minus the friction force, that's down the plane, minus this bottom component here, minus m2g sine theta. And we know that this object is accelerating up the plane because m1 is going to come down this way, so it's going to drag m2 up the plane. So the net force is in the positive direction here, so m2a. Okay, now the friction force, the definition is mu times r, okay? And so that will be, we found that r is m2g cos theta, so mu times r will be mu times m2g cos theta. So that this equation 2 here becomes T minus mu m2g cos theta minus m2g sine theta is m2a. Okay, now just at the very top of the page, we've had from equation 1 that the tension minus m1 times g is equal to minus m1a. So what we can do is take the m1g onto the other side, so add it to both sides, and we get an expression for the tension. Now, between these two coordinate systems, the tension will be exactly the same. So the tension here from equation 1, this one, is m1 times g minus m1a. Now we can substitute that into here, into equation 3. And so 3 becomes, all right, 3 becomes m1g minus m1a minus mu m2g cos theta minus m2g sine theta equals m2 times a. Okay, now let's just rearrange that a little bit, and we will take M1A on this side over to the other side because they're both talking about the same acceleration. The string is inextensible. The block going up the plane will have the same acceleration as the block hanging over the edge and going down. They both have to accelerate at the same rate because the string cannot be stretched. It doesn't deform, it doesn't stretch in any way. Okay, so the tension is both in the string the same, the net force on the string on the top of the plane and the string hanging vertically is the same. Okay, the two masses have the same acceleration, so it's the 1A value for both. Okay, so we now have an expression m1g minus mu m2g cos theta minus m2g sine theta is equal to all that. And what we can do is we can take out some common factors. Well, on the left, the g can come out, and on the right, the a can come out. And then what that just tells us is that an expression for the acceleration becomes the right-hand side divided by the sum of the two masses. So divide through by m1 plus m2 on both sides, and we're left with the acceleration of the system. That's both blocks will have the same acceleration, is g times m1 minus mu m2 cos theta minus m2 sine theta all over m2 plus m1. For any system like this, you can apply that formula, but rather than apply the formula, try to make sense of what's going on and draw your own diagrams and make sure you understand. But this anyway gives you an overview. All right, that's it then.